Hello everyone, thank you all for attending this virtual presentation. I would like to thank Shakil Kadri and his colleagues at CCPS for inviting me to give this keynote lecture. My apologies that I couldn't be there in person due to various constraints. So Shakil and I decided that I'll do this presentation virtually, but participate in the Q&A after the talk live via Skype. So the topic is the opportunities and challenges that the recent developments in artificial intelligence affords for us in process safety. Now, AI in process safety is really not new. We've been trying to do that for about 30 years. So in my talk, I'll try to review some of the past work that has happened and then discuss the opportunities and challenges at the present and in the near future. So my goal is to present process safety and systemic risk in the broader context of socio-technical systems, and then particularly address about the modeling and automation challenges using AI. It's not a very detailed technical presentation. I'll present a broad overview of the concepts, tools, and techniques, and so on. But if you're interested in the details, there are two papers that I published, one recently, earlier this year. That's the one on the left-hand side of the screen on the promise of AI in chemical engineering, and the one at the right is a paper on systemic risk. So when we talk about models in chemical engineering, particularly process safety and process control related work, we generally mean the traditional emphasis, that is modeling the equipment and processes. So what you see here is a typical chemical plant, and here is a flow sheet of it. And we develop DAE models, that is differential and algebraic equation-based models of the individual units as well as subsystems and so on. But a chemical plant is much more than just a bunch of equipment and systems, because a plant contains other important ingredient, which is people who make decisions in real time at the shop floor, as you see here, or in the boardroom in the executive suite. So the role of human beings and their decision making become very important in addressing process safety. And so one should really view plant as an embedded system, a system that is embedded in this complex network of nonlinear interactions among the equipment, processes, people, incentives, policies, and environment. And you see that in this seven-layer network here, seven-layer pyramid here, where at the bottom we have the equipment layer, which is where the pumps and valves sit. Then comes the plant layer, then comes the management layer, then the market, regulatory, government, and societal layers. So to address process safety and systemic risk properly, one needs to take a more comprehensive perspective along the lines shown in this pyramid. So how do we do that? And before we jump to that, I just want to highlight this particular aspect of process safety and systemic failure in complex socio-technical systems, and that usually systemic failures are large-scale failures that are triggered by some event or a series of events, such as pump failure, operator error, or a rogue employee making a decision, and so on. And usually systemic failures such as the Bhopal, India, or the BP oil spill, and so on, are usually accompanied by failures at different layers, at all these several levels which we saw in the previous slide. And this is really a control problem, even though the control community hasn't typically looked at this in that perspective. For example, the typical view of control, process control, the typical academic view is to develop some dynamical models of a process system. We talk about Laplace transforms and transfer functions, body plots, and poles in the right half plane, and so on and so forth. So these are the kind of things typically we teach in an undergraduate process control course. I taught such a course for nearly 20 years at Purdue and for several years here at Columbia. But how does control look like for an operator in a control room? So if you look at an operator's perspective, what would be a day in the life of a plant operator? So where this person is in a control room looking at a control board, hundreds of real-time information is coming in from various sensors, such as temperatures, flow rate, concentration, pressure, set points, and so on and so forth. So what would control look like for this guy? Now let's say that on this day, pump A is pumping oil and it has tripped. The cause is unknown. So you switch to pump B. But in a few minutes that also trips and the cause is unknown. Pretty soon hundreds of alarms go off and you don't know whether they're all related or they are independent causes. And within minutes you have an explosion and a fire and 2 people are killed and a few hurt. Now, to make matters more interesting, it's 10 o'clock in the night and you're desperately trying to reach your plant manager who was last seen in Aberdeen, Scotland and unreachable. And to make it even more challenging, you are on top of an offshore oil platform such as this one. You are the shift supervisor. What do you do? So now you have a process that is out of control. You have a control situation. But none of these things that you were taught in a control course, such as Laplace transforms and transfer functions and poles and right of plane, none of these things are of help at this point. They're completely useless to address this control problem in real time. Now, can such a thing happen? Or is it something I made up to drive home this point? Now, as it turns out, unfortunately, not only such things can happen, they did happen. In fact, these were the initial events, the early sequence of one of the worst ever chemical plant disasters known as the Piper Alpha disaster, where that offshore platform that I showed in the previous slide exploded to look like this in a matter of hours and killed 167 people and caused $2 billion in losses. So when such things happen, when the alarms go off, the operators want to know in real time answers to questions such as this. Now, what are the abnormal causes which cause this? What are the adverse consequences? Once the early events happen, you would like to know how this event sequence is going to proceed and what are my actions? How can I bring the process back into control? And if you were analyzing this in the design stage during process hazards analysis, you would like to know what your design choices are to avoid such an event and so on and so forth. So what is missing is the causal knowledge. And that is missing in the traditional control models. So how do we model this knowledge? It requires an entirely different approach to process control, typically not taught in our courses and typically not addressed even in the control research literature. But it complements the traditional control perspective. So the traditional control perspective is important, but that's only one side of the coin. The other side of the coin is building the causal models. And that is basically the challenge my students and I have tried to address for the last 35 years using AI. Our goal is to develop these intelligent control systems, which I see as the next frontier for automation in control. And that's where AI plays a major role. So how do we do this? This is where the various modeling choices and options come into picture, which are captured in this taxonomy. And basically there are model-based methods and process history-based methods we can do towards this automation. And each one of those has a quantitative and qualitative component similarly on this side. And it is in the causal models area, expert systems, and the neural networks and statistical approaches. And these are the places where AI can help us. So one of the things we need to develop towards this intelligent control system, operator advisory system kind of future is to be able to develop multi-scale models. That is, if we can take an entire plant, can we systematically break it down into smaller and smaller subsystems and units, and then develop causal models for them. For example, here is a sour water stripper, which is often a part of a refinery. That's the plant level view. And when you zoom in onto any particular unit, then you have a subsystem level where a bunch of units are connected. Then you zoom in further just to look at this tank. And so the idea is to develop the cause and effect relationships between the various variables and parameters at this level, and then build such models for all the units. Typically, it will be of the order of a couple of hundred such units in a library of causal models, and such that when you draw this flow sheet by hooking up these, by linking all these units, the causal models, the underlying causal models, also get automatically linked up so that you can do then cause and effect reasoning. So we demonstrated how to do these things in 1995, and then we also showed how to combine these things with recipe-based approaches, for example, which is useful in startup and shutdown of chemical plants or in batch processes. And so here is a recipe Petri net. This is a Petri net that models a sequence of tasks. And here you are doing reaction, filtration, and drying. And then when you zoom in on the reaction, it has a series of subtasks such as charging material A, charging B, heating, and then emptying, and so on. And then each one of these operations actually has a set of variables associated with it, which have causal interactions, which are all represented in the form of digraph. And so we showed how to do these kinds of things some 20 years ago. And such ideas were used in this consortium called ASM, Abnormal Situation Management Consortium, that Honeywell led between 1995 and 2000, with participation from a number of oil companies. This was funded at the level of $17 million at the time, half of which came from the NIST program of the US government, and the other half came from contributions from the oil companies. And there were 3 universities involved. And it was Ohio State, Jim Davis's group from Ohio State, my group from Purdue, and Kim Vincente's group from Toronto. This program is the forerunner to the Smart Manufacturing Initiative, which got funded a few years ago. The goal of this program was to develop this intelligent control system that I described in the previous slide. When the alarms go off, can it interpret the alarms and provide diagnostic guidance to the operators and so on. So as part of this, we developed at Purdue a system called Diagnostic Toolkit, or DKIT, which had this following blackboard architecture. It had models based on diagraphs, observers, trend analysis, expert systems, and neural networks. And they were all looking at the same real-time data coming in from the process and making individual assessments about whether the process is functioning normally or abnormally. And if it is abnormal, what might have gone wrong, and what are the causes, and what are the consequences, and what are the options. And it also used the trend analysis, for example, used techniques such as this one, and then we combined PCA with the digraphs so that we can provide explanations about how the diagnostic reasoning was carried out. So DKIT was implemented in an expert system environment called G2, and was tested on an Exxon refinery, Exxon chemical plant at Baton Rouge, and it successfully anticipated and diagnosed several failures even before the alarms went off. Typically half an hour to 2 hours before the alarms went off, even before the operators recognized there was a problem, DKIT was able to do incipient fault diagnosis and successfully so. So this got everybody excited, and so Honeywell decided to license a DKIT from Purdue in 1998, some 20 years ago, with the idea of commercializing the tool to scale it up for industrial implementation. So it was tested on industrial thing, but it was still a research prototype. So what happened? Why didn't we hear about DKIT after that? Well, it turned out that implementation and scale up and organizational challenges were quite insurmountable for that period, because the hardware support and the software support and communication, those kinds of things weren't there. And so the research prototype, what worked in the research prototype didn't work that well in a large-scale implementation. And so looking back, I realized that we were about 20 to 30 years too early to attack this problem for industrial impact. Even though we knew how to solve this problem, we knew how to develop these AI-based systems for file diagnosis and alarm advisory purposes and so on. For industrial applications, we were just too early. Now, what I've discussed so far is this inverse problem, that is going from symptoms to causes. The alarms go off and you're trying to figure out what happened. That's the ASM problem. And that's the diagnosis problem. That's the real-time problem. Now let me talk about the forward problem. That is, if I were to ask, these abnormal causes occur, what are the adverse consequences? That is the prognosis problem, also known as the process hazards analysis problem. This is what you do when you design a plant and then do a process hazards analysis. So we developed an expert system to do that as well. So we called it PHA Suite. It was developed over a 10-year period. And it's an AI-based system. It had a library of models, as you see here, and about 100 such models in the library. By hooking up these things and by creating a flow sheet here, you automatically hooked up all the underlying causal models in digraphs and Petrinet forms. And it had a reasoning engine where you can create any upsets in any one of the units, and it will propagate throughout and figure out all the causes and consequences. And we tested it on 20 real-life case studies, including pharmaceutical applications, and it typically captured about 95 to 100% of the human team's response, but typically in half the time and effort and money. And it was the first comprehensive PHA automation tool that was developed using AI, had about 35 man-years of R&D and software engineering effort, and about 500,000 lines of code. So it would display the results in this form. You can get a HAZOP table out of this. You can analyze it in so many different ways, unit by unit or line by line or by subsystem level or by the types of failures, all kinds of control it gave the user. So, and then we went further to show how a PHA Suite can be actually put online and used for real-time applications. Because typically when alarms go off, many of those causes and consequences have been anticipated, and they are in part of the PHA or the HAZOP results. But they are not available online real-time because they are usually in a binder sitting on some on a shelf in a plant somewhere. And so here we showed how to actually put that thing online, and when the alarms go off, the right part of those results are pulled up and provided as advisory to the operator. So let me talk about systemic risk a little more, and then also in a broader context. Such systemic failures, such as Piper Alpha, is not unique to the chemical industry. Similar failures have happened in other industries. For example, in the aerospace industry, we've had the Challenger and the Columbia Space Shuttle disasters. Johnson & Johnson had to recall 100 million bottles of children's Tylenol due to a quality control issue with their supply chain. The power failure in the Northeast is one such systemic failure. And of course, the financial crisis in the finance domain is another such failure. And so at Columbia, I direct a center called the Center for the Management of Systemic Risk with faculty from a number of different schools, where we are interested in studying these systemic failures in different domains and then compare and contrast in order to understand the common underlying mechanisms such that we can better design, control, and manage systemic risk going forward. So towards that goal, we have developed this 7-layer modeling hierarchy, which I showed in the earlier slides in the form of a 7-layer pyramid. Now each one corresponds to a layer here, and each one you can actually develop models to capture the phenomena of that layer. And so it goes from the equipment layer at the bottom all the way to the societal layer at the top. And we have a unifying control theoretic perspective for each one of those layers. So each one of the layers can be modeled using this kind of a feedback control kind of a block diagram approach. So where M is for a measuring device, C is the controller, V is the valve or an actuator, and P is the process. And using the same unifying structure layer after layer, we are able to actually systematically analyze what kind of things can go wrong at different layers in a complex system, and then compare them across domains as well. And for example, this is how typically you see that block diagram in a regulatory control framework, where you have a sensor, a controller with a set point, then the actuator and the process with disturbances coming in and so on. But it turns out the same thing can be applied to the management layer, where the sensor is replaced by performance monitoring systems you would have at the management level. The management access the controller. The management set points are the various production and profit goals you might have, which create the policies which are executed on the corporation. And similarly, the same structure can be applied to the regulatory view as well. So this unifies all the 7 layers and gives us a common modeling perspective. And these are, the models at the bottom are, DAE models, as I mentioned, but at the middle, you cannot write down equations because the players here are mostly humans. And so the best you can do are graph theoretic models, which capture cause and effect relationships, or agent-based models and game theoretic models. And then, so using this kind of a unifying framework, we are able to study systemic failures across different domains. And we studied 13 major disasters in the last roughly 30 years. And by carefully analyzing the reports produced for each one of them typically produced a anywhere from 300 to 500 page report. And then we studied them, and we tried to understand what were the mechanistic causes, what happened which led to this particular disaster, and so on. So we carefully reviewed such official postmortem reports. We ended up analyzing some 700 plus failures, which we categorized into 5 primary classes and 19 subclasses. And these classes were identified by using that control theoretic framework I showed in the previous slide, that the monitoring, there are certain monitoring failures that seem to happen across domains. They are very similar. Similarly, decision-making failures, action failures, and so on and so forth. So we were able to compare and contrast and identify that there are some common patterns that we can look out for in the future, and then catch these things early on, and then take the appropriate control and management actions. So to summarize, there's been a lot of work on AI for process safety. It's, as I said, people have been working on this for about 30 years, from the 80s onwards. And great progress were made in developing successful AI prototypes, which were demonstrated both for online applications, such as the real-time fault diagnosis applications that DKIT demonstrated in 1995 to 1998 timeframe, and the offline process hazards analysis or HAZOP analysis kind of applications that were demonstrated also around the same time. But why didn't AI then have a big impact in the industry? As I mentioned, it's due to mostly implementational and organizational difficulties. We simply didn't have the computational power in those days, and the storage. Communication infrastructure was largely absent. The software environments were much harder to work with compared to what is available now. Lack of data, and there was a resistance to computer advices in those days from people, and of course the costs were prohibitive. And essentially just took too much time, effort, and money to field industrial applications in those days. And like I said, we were about 20 to 30 years too early. But now it's different. I'm really excited about the prospects for AI, because many of these difficulties have largely gone away or greatly diminished, particularly in the last 10 years. And but so that got, having said that, I still think there are 3 classes of problems that we need to work on. Category easy, so these are the easy problems or easy applications, which are routine applications and that can be done now. So these are problems where large amounts of data are available, and that easy-to-use machine learning tools can be trained on them. So these are problems such as equipment health monitoring, preventive maintenance, and these kinds of things are already happening. And there are various companies, large and small, which are developing such products. Now that brings me to the next level of difficulty. These are problems which are harder, and I think they'll take another 10 years or so to learn to do them well and systematically. And these are problems which require developing AI models, hybrid AI models. That is, they part first principles based and part data-driven or data science-based. And this is where the causal models that generate explanations and so on come into picture. We demonstrated how to do these things 20 years ago, but it is still requires a lot of work, and then we need to develop the infrastructure and templates where we can develop such things much more reliably and much more quickly. Harder still are these problems, which I think are in the time frame 10 to 20 years out to do them well. And these are the Watson-like systems for process safety, where we have to develop domain-specific ontologies, domain-specific languages, compilers, and so on and so forth. So let me thank a whole set of students and postdocs and colleagues who have worked on the various aspects of this work I summarized in the last few slides, and various funding agencies over the years. And some of the images were taken from the internet under the Creative Commons licensing. And let me stop here, and I'm more than happy to take any questions you might have. Thank you.